Welcome to the Interface program. Today we have Professor Ramaprakash from Inter-University Center for Astronomy and Astrophysics, Pune as our guest. He has been involved in many astronomical instrumentation projects involving many countries. A warm welcome to Professor Ramaprakash.
Thank you, Ravi. It's a great pleasure to be here with you today, and I look forward to having a good chat with you.
So, as I know that you are coming from an engineering background. So, how do you develop basically astronomy and astrophysics and your interest in astronomy and astrophysics, or how did you end up in astronomy?
Yes, it's a interesting question. To be honest, I think it was also all a coincidence. Once I did my electronics engineering from College of Engineering, Trivandrum, in 1992, and the only decision I had made at that point was that I am not going to be an executive in a company or working for an industrial job. I wanted to continue in academics, but I was not clear at that point what area I would like to work on. I was exploring various options, and it so happened that I ended up in astronomy. And astronomy is always a fascinating field, and anybody who has any interest in science, technology, will immediately get attracted to astronomy. The moment you go by anywhere near it, the attraction of astronomy pulls you in, and I fell into it and I fell in love with it, and now I am an astronomer.
And second thing, actually, the area you are working is astronomical instrumentation. That also is not too popular, or I should say it was a courageous decision to get into it. Can you elaborate the activities that you are doing at IUCAA?
Yes, so let me give a little bit of background to that. In IUCAA or any other astronomy institutes in the country, usually people come from MSc background, mathematics background, and science background in general. But it is not unusual to have people coming from other backgrounds like me. With electronics engineering, there are mechanical engineers, software engineers working in astronomy. So astronomy is a field which requires talent from every possible pool, especially in today's world where the instruments used for astronomy, like the telescopes, the spectroscopes, they are very complex, extremely technically challenging instruments to build. So it requires people from all fields. Now, if you're going back to my specific case, when I started working for a PhD in astronomy at IUCAA, I had to also take an MSc, because that was a requirement that if you do not have a master's in physics or science, you cannot get register for a PhD in astronomy. So this forced me to take a master's in physics, MSc in physics, as well as then move on to a PhD in astronomy. The advantage it gave me is tremendous. It was very difficult at that time when I did that, but the advantage it gave me was tremendous, because if you have a specific problem to solve, the way a scientist would look at that problem is very different from a way an engineer would look at that. A scientist would like to have a theoretical understanding of the problem, the general class of problems, the solutions to general class of problems, and then have a top to bottom approach. On the other hand, an engineer is most concerned with solving that problem without really worrying about what is the global picture, what leads to that kind of situations in general, and so on. I want to solve this problem, I want to make progress, I want to deliver my product in time. So that's a different approach. So the same problem is viewed by these two groups of people differently. And I must say I am able to sort of bridge the gap between these two groups. When an engineer speaks about a problem and a scientist speaks about a problem, they might be speaking about the same thing but different languages in practice. and someone to bridge that gap and translate a scientific requirement to an engineering problem and then solve it, and then get the data required for the scientists to understand the situation. That's I think where my role in general fits into the overall scenario of things, and I think that's a niche area, and so I'm glad that I did that at that time. I was forced to do that, and I did that, and it is helping me a lot in general.
Okay.
So coming back to your specific question about what kind of activities we do in the instrumentation laboratory at IUCAA. IUCAA's lab started out as a small facility. Even now it is a small group by laboratory standards, like a CSIR lab or a big facility in particle physics. It is a very small lab, about 20 people work there. But we identify very niche areas and then try to use technology which is becoming available now to push those niche areas and find applications for that in astronomy, so that you can do unique things.
And that too in a global fashion.
In a way that it is attractive internationally or globally. So we try to specialize on those kind of things rather than trying to do many things at the same time and make slow progress. We try to identify. Three specific examples I can mention are any astronomy system requires sensors, because astronomy is all about sensing light or other radiation coming from distant sources. So you use telescopes to collect the light. The telescope is only a light collecting bucket, and it brings the light to its focus. At the focus you need various kinds of optics and sensors which can translate that light into information which an astronomer needs. And these sensors are very expensive and exquisite components of an instrumentation system. So we specialize in developing controllers for these sensors to acquire data from the sensors, the electronics, the software for these sensors, which are not many groups around the world are experts in doing that. And we specialize in that, and our controllers, our sensor controllers are used in almost all big facilities around the world, big observatory facilities around the world. Similarly, we develop technologies using optical fibers for applications in astronomy, very unique applications for spectroscopy. What is called hyperspectroscopy or two-dimensional spectroscopy and so on, area spectroscopy. We use adaptive optics to improve the quality of data which you can get from astronomical telescopes. So there are these very specific niche areas where we develop technology in the lab and apply it to astronomy to get a unique instrument.
Yeah, since you were talking about adaptive optics, will you be able to explain it a little bit more, because not everybody will be using or understanding it?
Okay, I will try to. It is a very complicated optical system, but I will try to explain it as a few words as possible. We all probably have come across adaptive optic systems in our lives, almost all of us. For example, if you are someone who wears spectacles and you go to a shop to get your eye tested, the doctor there usually nowadays have an automated machine. He will ask you to look through the machine, and in the machine you will see some things going back and forward and then coming to focus and adjusting. So that equipment is measuring the eye's response to certain signals coming in and reacting to it and adjusting, and then in that process trying to measure the performance of your eye, and then trying to figure out what compensation you need using spectacles. So this is adaptive optics, and that optics is reacting to a system and try to adjust for it and compensate for it so that you can measure it. In astronomy, what happens is when light comes from this very faraway objects like stars, galaxies, etc., most of the time light is passing through space, and space is basically empty. So the light just passes through the space, and that's how it arrives on Earth. But once it comes above that Earth, there is atmosphere, and the atmosphere has a lot of particles, oxygen, dust, other particles in the atmosphere, nitrogen. And as light passes through the atmosphere, the light is affected because the atmosphere is not very stable. It's a turbulent medium. It is changing very fast. All the time the atmosphere is changing because human activity going on, winds are blowing, or the sun is heating the atmosphere, Earth is rotating, all kinds of activities. So the atmosphere is not a stable medium. The light has to pass through this medium, and because of the turbulence in the medium, the image of the object you are trying to look through a telescope gets blurred. It becomes sort of, I wouldn't call it defocused, but blurred. Now, this is a serious limitation to do in astronomy, because then you cannot see very fine details of objects you are looking at because the light is blurred by the atmosphere. So, adaptive optics uses lasers to measure the instantaneous effect an atmosphere has in the light as it passes through from your target, and then use some optics to compensate for it, so that the effect of atmosphere is nullified by as much as possible in real time. So, it's a continuous process in real time, and that is of tremendous application in astronomy, because all major telescopes, observatory facilities will have adaptive optics to compensate for it, for the atmosphere. The only other option is to go to space above the atmosphere, which is very expensive, and an observatory on a ground-based observatory, you can maintain it for hundreds of years, maybe 100 years. You can, as technology improves, you can go and easily upgrade it, put new instruments there. But space-based telescopes have a limited lifetime, 5 years lifetime, 10 years lifetime. They are very expensive, and if you have to repair anything, it's not easy to send someone up there to repair or upgrade and so on. Yeah. So these are complementary. So if you have to completely nullify the effect of atmosphere, you go to space. That is expensive and can do very specific things. But if you want a general purpose, long-standing observatory, you build one on ground and then maintain it for a long time. And also, if you want a 30-meter diameter telescope, which is very, very large, you cannot launch it into space. It's impossible. No, modern technology cannot do that. So they have to be on ground. So there are merits and demerits for both approaches. So there are many ground-based telescopes, and there are space-based observatories also.
Yeah. Coming back to the instrumentation scenario, how tough is the, or how in general, what is the basic requirement that you are asking from a student to get into astronomical instrumentation, say?
Okay. This is very interesting. In general, if you want to come to astronomy, what one is looking for is an good understanding of physics, mathematics, and related subjects, which you study as part of a science curriculum. That's what is usually required to work in astronomy. If you want to involve in building instruments for astronomy, you can always you can be coming from an engineering background, or even if you come with a physics background and you are good at experimental setups, making equipment, playing around with hardware and software and things like that, you can always pick up those skills. So I think a basic skill at a master's level in physics, mathematics, and an ability to, or an interest in making things and even breaking things while trying to make them, and that is what is essentially required. An engineering background is not essential. But as I said earlier, if you have a basic training of engineering, the way you would look at problems could be different, and then you could play that role, but that's not essential. There are mechanical engineers who are doing very high-end theory in astronomy. There are engineers who are doing numerical simulations in astronomy. There are scientists who come from physics background who are building instruments in astronomy. So it is a need-based and an interest-based science. But you have to be good at what you are trying to do, and you must have a drive to do this, solve difficult problems, and push things to their limits, and don't give up easily. That's basically what you need. And once you have that attitude, I think you can do what is required for astronomy. It's not the background is not so
the drive is
important. You have to be good at what you basic science or engineering is, but then you can pick up what is required. Okay. That's my expression.
Okay. That's actually a good thing, because if you have the drive, then you can definitely come up.
Exactly. So that's what I feel. Okay. The background is important, but it's not a dominating factor. The drive is a dominating factor. I want to do it. That's what should be there.
So coming, what are the major opportunities arising nowadays for a student to look forward in astronomical instrumentation, say, or in astronomy in general?
Yes, I think we are in a golden age in astronomy at this point of time. So all those people out there who are doing their bachelor's or master's, this is the right time to get interested in astronomy and see if you can contribute to it, because around the world there are many massive new facilities coming up in astronomy. Like the 30-meter telescope is an example where India is participating. There is the square kilometer array, which is a radio telescope. Again, India is participating. And recently, many of you would have heard about the gravitational waves and the first detection of gravitational waves. And one of the next advanced gravitational wave observatory is planned to be set up in India. And if you look at many of these programs, India is making an active participation in many of them. So it's a golden time for students to understand what these projects are and develop interest in them and contribute to that. And it is a wonderful time to be in astronomy. So I'm sure there are many opportunities for physicists and scientists and engineers to contribute to various facets of this facility building which are coming up. They could be ground-based, space-based, all kinds of wavelengths from gamma rays to radio waves. The facilities coming up all over. So the next decade is going to be a decade of discoveries. These facilities will become operating and after about 5-10 years of time. They are complex facilities, so they require 8 to 10 years to build. And once they become operational, they will ask some of the most fundamental questions you can ask. For example, questions like, is there life anywhere else other than Earth? Can we see evidence of life anywhere else in Earth, in the world? What is the overall structure of our universe in which we live in? How do these galaxies and stars which we see, how them form, and what kind of structure do they look at in the large scale? How do black holes form, supermassive black holes form, and how do they evolve? All kinds of fundamental questions which you can ask will be addressed by these facilities. So it's a golden time. Right. If you look at the way astronomy has progressed, there were millennia when after people started looking at the sky with the naked eyes and recorded movements of objects in the sky and try to understand patterns of movements and so on. Millennia passed, and only about 400 years ago someone had the thinking to use and point a telescope to the sky Galileo, and it opened up a new world. It opened up unimaginably new things for us to understand. For example, it told us that instead of the Earth being at the center of the universe, it is the sun around which the Earth is going around, and the planets are going around. Sun itself is not a blemishless star, it has sunspots, all kinds of new things. Similarly, when these small telescopes were being used and in operation, that happened for several hundred years, and technology improved. And when 1 meter size aperture telescopes started being made, it was the 1 meter class telescopes which told us, the observations using 1 meter class telescopes which told us that our universe is expanding. So this is unthinkable at that time. How can the space itself expand? There was concepts or a theory behind it, but it is not clear whether it's an expanding universe, it's a steady universe, what happens after a long time, or what happened a long time in the past. So the idea of an expansion of the universe came with 1 meter class telescope. Similarly, every time a technology leap happens and new facilities come up, new windows into the universe open up, unimagined new discoveries are made. That's what is challenging, that's what is interesting, and that's going to happen in the next 10 years. Many new discoveries. So it's the right time to be in astronomy.
Well, how does our research, especially the standards of astronomical instrumentation, stand with regard to this that is available in the country, in the world?
Okay, so there are 3 answers to that question. So let me tackle that one by one. If you ask me how theory is going on in astronomy, theoretical developments in astronomy, I think we are doing very well. So theory requires, we have a tradition of doing theoretical things and doing theoretical developments. Chandrasekhar, Saha, any number of names, even in the new, we need not go to Aryabhata's time. Even in modern times, there are many stalwarts coming from India who have done path-breaking theoretical development. So in theory, we are doing pretty well in the international scene. As far as observations are concerned, observational astronomy require facilities like large telescopes, very complicated instruments to carry out those observations and analysis of data and so on. That is not exactly at the same level as theoretical stage, basically because in India we do not have large facilities comparable to everywhere else in the world. As an example, when India built a 2.3 meter Venu Bapu telescope a few decades ago, the largest telescope in the world had an aperture of 4 meters. So we are competitive. So 2 meters, then we can always think of making the next level of progress, and we could do. We are only one step behind. Fast forward several decades to today, the largest telescope in India today is a 3.6 meter telescope, and that was commissioned only a few months ago. To go from 2.3 meter telescope to a 3.6 meter telescope in our country, it took decades. In the meantime, the world has progressed from 4 meter class telescopes to 8 meter class telescope to 10 meter class telescope. Now they are building 25-30 meter class telescopes and even thinking about 100 meter class telescopes. So the facility gap is huge, and that is limiting our observers from competing at an international level. Individual observers who have collaborations and have individual access to these facilities manage to get the data they need to do their observational astronomy, but it's not done on a systematic way. I think that it is high time that we change that approach. We put in place a systematic process by which institutes and astronomers in this country can have access to the best facilities in the world, and only then can we compete meaningfully on a global scale. So, that is required. Now, on a longer time scale, the difficulty is that not many people are interested in building facilities. To build facilities, we need to learn how to build instruments. Instruments, a collection of instruments become a facility. To build instruments, we need to develop technologies. Now, a lot of effort is spent in India to develop technologies. We have the nano mission, biotechnology, you name any new technology, we have a mission to excel in that. But very often these technological developments which happen in our labs are not translated into applications which are usable in different fields. That gap is not getting
clear,
bridged very easily. So, we do develop technologies, we do develop the theory for those technologies, but we do not convert those technologies into applications in real situations, and that is something which we need to address. In astronomy specifically, we find it very difficult to attract students who want to build facilities and make instruments and build facilities, and that is something which we need to address very rapidly, because we cannot go on observing time on facilities which somebody else has built. We need our own observing time.
Yeah.
We need to build our own facilities so that our own astronomers can use the telescopes and the facilities the way we would like to use it. So, that requires building our own facilities, and for that we need to have a set of people who are willing to spend their time to convert the technologies into new applications and instruments, and then those applications and instruments to facilities. That is a long term requirement, and that also we need to start now. So, both aspects. In the intermediate time scale, we need to get immediately time in existing large facilities for the current crop of astronomers to push their science forward. And in the long run, we should invest heavily in building facilities in the country or at the best places in the world, but the facilities have to be conceived and developed by people in the country, or at least led by groups in the country in collaboration on an international scene. That, unless that is done, it would be very difficult to sustain a competitive scale of activity in the country. The theory may continue, theoreticians get data from others' observations and they can continue to develop their theory, but they also need to be inspired by observations done by my friend here or a colleague there who made a new discovery, and I need to be challenged to find a theory to explain that new discovery rather than finding a theory to explain somebody else's discovery somewhere else. And so that has to go hand in hand, the instrument building, facility building, using those facilities to make new discoveries, new ideas, and then the theory to explain that they have to progress together. But we have a 3-level thing. Theory is doing well, observations not so well, facility building nowhere in the international scene. That's a difficult situation.
Yeah. So, it was very wonderful to talk to you, Ram Prakash. Thank you for coming to the Interface program.
Thank you very much. It was a pleasure.